Now see, we have already discussed the forces on moving charges. Now let us discuss the forces on current carrying conductor. So if there is a current carrying conductor, inside that also there are moving charges. So if charges are moving in that, that must also be experiencing some force. So we will be saying that in case of a current carrying conductor, in the magnetic field, force experienced by a small elemental length, that is small elemental length is this dl, which is basically, this is the dl vector, which is same as the direction, and direction of this dl vector is taken as what? Direction of the current. Okay, so if our current is flowing this way, then we'll say dl is having this direction. The small force df is given by this expression. How this expression is coming? So I'll be saying that if there is q charge from here, moving from here to here in t time, then I will be saying that force on that charge, moving charge, is nothing but how much? The QVB. So force or small force on that moving charge is nothing but Q V cross B. Now what I am going to do is I am writing velocity vector. Velocity vector is what? See, velocity is the distance traveled, which is dl divided by the speed, and direction is same as dl vector. So I am writing that v vector, the velocity vector, is the distance traveled by the time taken. Time taken you can take dt, right? So it is basically dt and cross b vector. So now I am simply taking this dt out. So charge upon dt, the charge divided by time taken. So q charge is flowing from here to here in dt time, and that's my what? Current. So I'll get dl cross b. So if you see the first expression, that is nothing but I, right? This is current, the charge upon time, right? And this is dl cross b. So that's your expression for df. Generally we remember this expression in this manner. For L length, it is I L cross b. And L cross b means L b sine theta, where theta is angle between L vector and b vector. Let us utilize this. So IDL is called current element. Okay, so here this IDL is called current element. And now let us discuss the direction. So direction is dl cross b, right? So dl is in the direction of current, and you don't need to do the cross product. So there are two examples. Here the current is flowing in this direction, so dl is that way, and you need to turn your right hand in the direction of towards b. So curl your finger towards b, right? So you'll see up. So here the force is in upward direction. Again, if you have a look on this diagram, here the IDL is that way. So if you put your finger in the direction of IL, turn them towards B. See, if I turn it like this, I cannot turn it towards right. So keep in such a manner that your palm is facing the other vector, the B vector, right? And direction is downward. So the force, the DF, small force, is in downward direction. And the force on a longer wire is ILB sine theta, which we generally remember as BIL, Bill sine theta, right? So here there are basically force on a straight current carrying current wire is F is equal to IL cross B, which is, if you just want to remember, it is ILB. I would suggest that remember it is like ILB sine theta, not some of these students, they remember it like Bill sine theta. But when you remember it that way, the vector, these two vectors get exchanged. And if this vector, our order is changing, then basically the direction of force will be other way around, right? So make sure that it is L cross B. That's why it is suggested that you remember ILB, not BIL, right? Next is force on a bent conductor, current carrying wire. So if we have a current carrying wire, but that is not a straight wire, it is like this. So current is going this way. Now I will be saying, suppose like this to this is my point A. The wire is AB, and the I current is flowing in the wire. So how much is the force on a bent wire? So we'll be saying force on a bent wire is also ILB. It's just we use effective length. What is effective length? Effective length is the length which is starting from starting point and ending at ending point. So this AB. So this is your effective length, and this is the L effective vector. Okay, so instead of just L vector, use L effective, use the effective length. Okay, how this is coming? Basically, if we are talking about DF, then it is I DL cross B. So in case I want to find the total force, so I'll be simply saying do the integration. So here it will be total force, right? Vector sum of all these small forces is going to be the total force. I is a constant quantity, and here the magnetic field is also uniform. So this integration dl is what? The total L effective. See, when you integrate such small length, so when you add them vector wise, you will get the total lengths. When all these dl add up, we will get this length AB, right? So that becomes L effective into B vector. So we can remember this formula where the L effective is effective length of the bent wire. Okay, starting from starting point up to all the way to the other end. What if A and B? What if we are talking about a loop? So for a complete loop, current is flowing in a loop like this. So I am saying how much is the force? We'll say, so I am just treating it as a bent wire. So from A to B, A and B are eventually same point. So the effective length is 0. So if effective length is 0, then the force experienced is also 0. So we can conclude that force experienced by a loop, current carrying loop in a uniform magnetic field is 0. We'll also discuss this in a later section. Now there is a question. So this question says a straight wire of mass 200 gram and length 1.5 meter carries a current of 2 ampere. So there is a wire which is having some length and carrying some current. Now it is suspended in mid-air by a uniform horizontal magnetic field B. What is the magnitude of magnetic field B in Tesla? So we'll be saying if this is a wire and you are suspending that in mid-air, so there must be, see, here the mass of the wire is given. So mass is 200 gram. We'll be saying the force is basically mg. Who will oppose this mg? Due to mg, it is in mid-air, right? So it will fall. So there must be the upward force, and that must be the magnetic force. And how much is the magnetic force on a current carrying wire? It is ILB. IL cross B, that is to be precise. So we'll be saying just the magnitude is L cross B. If you see L cross B, so length is either this way or that way. That depends in which direction current is flowing. So L vector is horizontal. What about B vector? B vector, they are saying uniform horizontal magnetic field. So if horizontal magnetic field, see, L is horizontal and B is horizontal, but other way around. If that is not the case, then what would happen? If they are in the same direction, then this force will become 0. If that is 0, then it will fall. So we are taking the case where one is towards north or other is north south, and the L is towards north south and the other is towards east west. So that is, both of them are horizontal, but the angle between them is 90 degrees. So this value simply can be written as ILB, and I am equating this force to this force. Just equate them and get the answer. So ILB is equal to mg. So I am just putting the value and solving it for my B. B is my magnetic field required to make the wire suspend in mid-air. So that is mg by IL. The mass is 200 grams. So 200 by 1000. G is, I am taking 10. And IL, the current flowing is 2 ampere. And the length is 1.5 meter. So I can simply say, cancel this. It is 2. 2 is also cancelled. It is 1 by 3 by 2. So it is 2 by 3. 2 by 3 Tesla or 0.666 Tesla is the required magnetic field which can make this wire of 200 grams suspend in mid-air. Now, we are going to talk about, see, we discussed the force on a single current carrying wire in the presence of magnetic field. What will happen if there are two parallel wire, okay, two parallel wire which are both of them are carrying the current. So in such case, what happens is, here we have two parallel conductors. This is basically having a current of I1, this is having a current of I2. And now what happens is, this, just understand it like this. The first wire produces a magnetic field. Each and every current carrying wire produces a magnetic field. And if you see, there is a magnetic field in this region in which you are keeping the second current carrying wire. So it will experience a force. The other way is also true. If this is a current carrying wire, then it will be producing a magnetic field, and the wire I1, wire which is carrying the current I1, is kept in that magnetic field B2. So it will also experience a force F1. And now let us find these forces. So here I am saying this is my wire 1 carrying a current I1, and I am going just one way around. I will be saying the wire 1 is the one which is producing the magnetic field, and it is this magnetic field which is experienced by the wire 2. So let us find, first is, so how much is the magnetic field? If you see, the current is in the upward direction, right? So if current is in upward direction, by right hand grip rule we can say the direction of magnetic field here is going to be out of the plane, and at this point it is going to be into the plane of the paper. Now let us say it is infinite long wire. So if it is infinitely long wire and the magnitude at r distance is b, here also it is going to be, here also it is going to be b, right? So magnitude of magnetic field is b in all these points which are separated at r distance. This b is given by what? We already discussed this. The magnetic field due to a current carrying wire at r distance is given by mu naught I by 2 pi r. So this is the magnetic field which is produced by this wire, and here the I is what? I1. So I am replacing that with I1. And this is the magnetic field. Now let us keep the current, this second wire, in that magnetic field. So I am keeping this current carrying wire in that magnetic field over here. Now if you see, forget about the first one. Here we are keeping a current, like just forget about this one completely. There is a current carrying wire which is kept in uniform magnetic field. What is the magnitude of that magnetic field? B. B is mu naught I1 by 2 pi r. So a current carrying wire will experience a force, and direction is what? IL cross B. So L is which way? In the direction of current. Cross B, B is into the plane of the paper, and direction of force is going to be this way. So let us find the amount of force which is experienced by this wire. So I am saying, let's say it is experiencing F amount of force, and I am only talking about a limited region length, like from here to here only I am talking about, and let's say this length is L. So this length is length of the, I am only talking about L length of the wire, not the entire wire. Okay. So this wire is having L length, and this, on this L length, the force is given by what? The force is given by ILB sine theta. Let's just write all the values one by one. Current in the wire is I2. The length of the wire is L. The magnetic field is nothing but mu naught I1 by 2 pi r. And sine theta, the angle between L vector and B vector. Here the L vector is in upward direction while B vector is into the plane at this particular point, right? So the angle is going to be 90 degrees. So this is sine 90 degree. And when you solve this, you will get this expression as mu naught I1 I2 by 2 pi r L. And that's your force. So if this L comes here in the denominator, then we will be saying that our force per unit length is nothing but this. Why are we finding force per unit length? Because longer this wire is, bigger the force is going to be. So force per unit length is given by this expression. What about force on this wire? See, there are various ways to explain this, or we will say that when we are writing magnetic field at this region, it will be same expression mu naught I by 2 pi r, but it just that I2 will be coming here. But when you are finding writing ILB, this I will be I1. So again just I1 and I2 are replaced and result is still same. But what about the direction? Direction is going to be other way around. So see, the magnetic field due to this wire is, see, it due to this I2 wire is out of the plane in this region. And since it is out of the plane, here it was into the plane. So direction of force is going to be exactly opposite, the other way around. So on this wire, there will be a force capital F like this. And these two forces are equal and opposite. Okay, or you can also say like this, in the entire universe, there is nothing. There are only these two wires. If one wire is like applying capital F force per unit length, force per like this much force per unit length on the other, the second one will also apply the same amount of equal and opposite force, right? That's Newton's third law, action reaction. So one of them is action, one other is reaction. They are equal and opposite, and it is given by this expression. So we will be saying that both parallel current carrying conductors will attract each other. As you have seen in the figure, they were attracting each other with equal and opposite forces, right? Which are given by forces per unit length, which is given by mu naught I1 I2 by 2 pi d. I used R, but what is d? D is the distance between those two wires. Now here there are two cases. In case number 1, which we just discussed, the current are going in the same direction. There are two parallel wires and both are carrying current in the same direction. They will attract each other. But what will happen if the current in them are other way around, in opposite direction? Then rather than attraction, there will be repulsion. So you need to remember, current in the same direction, if two wires carrying current in the same direction, they do attract each other. While if current is in opposite direction, then what happens? They repel each other. So that's the thing which you need to remember. Now let us discuss this question. This question says that a conducting rod of mass m and length L is placed in the east-west direction on a frictionless horizontal table. The horizontal component of Earth's magnetic field is capital B from south to north. If charge capital Q is suddenly passed through the conductor, then find the instantaneous velocity acquired by the rod. So we'll be saying that this is my north-south direction. This is my west-east direction. I'm just keeping the direction sign. Okay. And then they are saying a conductor rod of mass is kept in east-west direction. So rod is kept in east-west direction like this, right? On a frictionless horizontal table. This is the top view. And then the magnetic field is acting from south to north. So this is the direction of magnetic field. And that is capital B in magnitude, and due to Earth's magnetism, this field is there. Now they are saying if Q charge is passing through it, right? Suddenly, let's say it is taking delta T time for Q charge to pass, right? And the wire is having M mass and L length. So this wire is having M mass and L length. Now they are saying what will be the velocity acquired? We'll be saying that since the charge is passing in a particular time, there is some current, and due to that current, there will be some force. Let us get that force. So I'll be saying force is nothing but ILB sine theta. So ILB sine theta. Let's just put all the values one by one. Current is how much? Current is Q by delta T. Length is L, B is B sine theta. The angle between L vector, which is in this direction, and B vector, which is in north-south direction, is basically 90 degrees. So I'm writing sine 90. And here I am taking, this is 1, this delta T is going other way around. So I'm writing F delta T is equal to QLB. What is F delta T? That's change in momentum, right? That's impulse. So I'll be writing that F delta T is nothing but impulse, or we will say it is nothing but mv minus mu, and initially it was at rest. So m into v. V is what? Final velocity acquired by that, minus mu, which is 0, is equal to QLB. And they are asking what is the velocity acquired by the rod. So let's say v is the final velocity acquired by the rod, and the answer comes to be v is equal to QLB by m. So this is the velocity acquired by the rod. Now next question is a wire ABCDEF with each side length L. Okay, so AB is L, BC is L, CD is L, DE is L, and EF is also L. With each side L, which is shown in the figure, is carrying some current I, and it is placed in the magnetic field. Okay, now they are asking what is the force on the wire. See, this entire wire I am looking at one by one section. Okay, so first have a look at section AB. So current is flowing A to B. The direction of B is also in that direction. So DL is in this direction towards positive y-axis, right? And L vector, right, it is same as the direction of current. So L vector and B vector both are in same direction. No amount of force will be acting in this direction. Angle here's ILB sine theta, theta is 0 over here. For EF, it is basically 180 degree, right? The DL is E to F, F to E, and the B is other way around. So angle between them is 180 degree, sine 180 is 0. So no force is experienced by EF this section. What about CB and DE? So here the DL is this way and B is this way. So I'll see L cross L towards negative Z, L cross B, right? So this cross B. So the force is going to be this direction. How much it is? It is nothing but BIL or ILB. I would rather write ILB rather than BIL. Current is ILB. And have a look at this section. So L is upward, B is this way. So force is going to be in this direction. So that force is again ILB. Now have a look. This force and this force, they are opposite and they are equal also. So on the overall conductor, they will cancel out the effect of each other. So they will cancel out the effect of each other. And what about this section? Now I'll say whatever is the force experienced by this section, that is the total force experienced by the entire wire, and that is again do L cross B, so upward. So there is an upward force, that direction is positive Z. So I'll be saying total force is ILB and the direction is positive Z direction. So it is ILB or BIL along positive Z, not the negative Z. Okay, so correct option is going to be A.